Now that we have a better idea about how our electromagnetic interference can move between different components, so we've looked at different transfer paths, we want to look at techniques to reduce this EMI. And so EMI issues can usually be difficult and costly to diagnose. So because of that, it's important to keep in mind these EMI reduction techniques while you're still in the design phase, so it can save a lot of time and money later on. So we're going to talk about a few such techniques. The first one, which we're going to focus on a little bit in this video as well as the next video, is filtering. And then a subset of filtering that we're going to talk about, and we've already seen a little bit, is bypassing. The two other techniques we're going to talk about later on are grounding and shielding. And so again, we're just going to touch on each of these briefly. We're just kind of introducing these high-level topics, and then if anything becomes relevant to where you're working later in your career, hopefully it gives you a good starting point. So let's start by talking about our filtering and bypassing. So in general, this filtering and bypassing is going to be primarily for conduction EMI. So primarily for conduction EMI, and so of course that's when we had some physical connection, some wire connecting our EMI source and our victim. And so let's sort of define these two things. So our filtering is actually the same sort of idea that we've seen in a lot of other classes. We're just blocking some undesired signal while passing our desired signal through. So we're blocking our undesired signal. So that's going to be our EMI, while passing our power or our signal, depending on our specific application. And so our signals can be AC signals, or they could be DC signals. And so again, this is sort of the same idea we've seen before. So based on a certain frequency, some things get passed, some things don't. Now a subset of that is our bypassing. So let me just write here that this is a subset of filtering. And so we've kind of looked at this before in a previous video, and we're actually going to come back to that circuit here in a minute. But what our bypassing is we're connecting some line that should be at a constant voltage to ground via a capacitor. So connecting lines that should be constant voltage. So oftentimes this is going to mean power supply lines, as we saw in a previous video. So typically this is power supply. So we're connecting these lines that should be at a constant voltage to ground, and we're doing that via a capacitor. And depending on the application, we might actually have multiple capacitors, and so we'll come back and mention that a little bit later on as we talk about sizing our capacitors for these circuits. So with that in mind, let's actually go back to that circuit that we had looked at in a previous video. And so here it is. So we had our 3-stage amplifier, and we said this third stage, A3, is some high gain output stage, and we have some non-ideal power supply which has this internal resistance R sub P. We said that if we didn't have this R sub P, that it wouldn't be any issue. But what happens is when we get some large signal on our output, we can have this an AC component of a current being drawn on the power line. And so if we have this R sub P, we then get an AC voltage V sub 3 on that power line. And so what we had looked at is we had looked at using a low pass filter. So we have a low pass filter here and a low pass filter here in order to allow a path for our AC signal to flow to ground. And so the same basic idea holds here, but actually let's take it a step further, and what we can say is that in general, anytime a circuit is going to be drawing AC power, or not AC power, but a current with a high frequency component, so let's say our solution to this problem. So anytime we have this circuit drawing RF energy, so anytime a circuit draws current with an RF component, so RF being radio frequency, So from a power supply, and again, we're never going to have an ideal power supply. Every power supply is going to have some internal resistance associated with it. What we want to do to fix this issue of having an AC voltage component that, if we didn't have this proper filtering here, could eventually find its way back to the input on A1. So how we want to solve this is we want to use a bypass capacitor, and we want to put it as physically close to, in this case, our A3 as possible. So we want to use a bypass capacitor, and we want this capacitor to be as physically close to our circuit drawing power as possible. So the key thing there is we want this bypass capacitor to be very close to our circuit. So what that would look like here is, if we know we have this AC component in our current I3, we can put a bypass capacitor in that power supply line very close to where that power is being drawn from our component. And so we'll come back and we'll talk about how to determine what value of that capacitor here in a little bit. And so, of course, we can see what this is doing is this is sort of nipping this problem in the bud, because as this AC current is developing here, it has this path to ground such that it's not going to be traveling up here. It's not going to be creating a time varying voltage, lowercase v sub 3, because of this internal resistance R sub P. So that's kind of the basic idea with our bypassing. So what are some circuits that would need bypass capacitors? So let's say, where do we typically bypass? And so we've actually worked with some of these circuits, and because we were just looking at ideal cases, we didn't get into this too much. But one example would be switching power supplies. So that would be like our buck converters, our boost converters, our buck boost converters. Any high-speed digital circuitry. So anything where we're switching and we have these impulses. So high-speed digital circuits. Radio frequency amplifiers, so like we saw in the example circuit that we just finished talking about. Also, any audio amplifier output stages. And so it's the same basic idea as the RF amplifier that we just looked at, because we're going to have some large gain stage for our output. And then also motor, LED, or display driving circuits. So motor, LED, or display drivers. So those are all instances where we would want to consider using a bypass capacitor. So coming back to this idea of, well, we know that we want this bypass capacitor to be physically close, but how do we determine what size we need? So how to size our bypass capacitor? And so, as I alluded to earlier, it kind of depends on our application. And so the reason it depends on our application is because, remember, our capacitor impedance is given by Z sub C is equal to 1 over J omega C. So with this, we can say it depends on the frequencies of the signals involved. So it depends on frequencies involved. So for instance, we could think of sort of two extreme cases. We could think of a lower frequency circuit. So if we have lower frequency, and or if we have some larger or voltage current magnitude, so lower frequency and a larger voltage current, then what we're going to want to do is have a larger capacitor. Because remember, ultimately we want this ZC to be a small value, because it's providing this path to ground, as we see here, for this AC component. So we want that to be as small as possible, that capacitor impedance, And so what we can see from this Z sub C equation, if we have a lower frequency value, that's going to be driving our impedance up. So we would need a larger capacitance value to sort of counteract that and keep our impedance value low. So on the flip side though, let's say we have a higher frequency or we have some smaller voltage current swings. In that case, we can use a smaller capacitor. So higher frequencies means we can use a smaller capacitor. And so again, it's going to depend a lot on application, but these are just sort of two general cases that we can consider. A lot of times as well, a useful place to see what size bypass capacitor you need is the data sheet for a particular IC or a particular circuit. So for instance, using a buck converter as an example, if you were to buy a chip that has a buck converter, the data sheet would be able to recommend a good value of bypass capacitor. So some typical values that you'll see recommended in data sheets. So typical, try to clean that up a little bit. So typical values are 1 microfarad would be sort of on the larger end for these electronic circuits that we're looking at. 0.1 microfarad is another common one, and then 0.01 microfarads. And another thing to keep in mind too is that maybe a particular circuit has multiple frequencies, in which case we might need to have different size bypass capacitors. So maybe we have a larger bypass capacitor to handle some of the lower frequency signals, and then we have a smaller bypass capacitor to handle some of the higher frequency signals. So we don't necessarily need to limit ourselves to just using one. The final thing we want to discuss related to our bypass capacitors is not all bypass capacitors are used to prevent EMI. So not all bypass capacitors are for EMI reduction. And so one example that we've seen in a previous class would be our common emitter circuit. So if we think about a common emitter amplifier, so in our common emitter amplifier, we looked at two configurations, and so let me come down here to this next page. So we have something that looks like this. And so in our analysis of this circuit, initially we did not have this capacitor C sub E. We calculated some gain, but then we went back and we said, if we add this bypass capacitor CE, it allows us to maintain our biasing from these resistors, and so this should be our RC. It allows us to maintain our biasing and keep that Q point steady while maintaining our gain. So basically, this resistor RE was helping to stabilize our gain at the Q point, or sorry, it was helping to stabilize our DC Q point. However, it reduced our gain. So by using this bypass capacitor, we're able to get the best of both worlds. If you want to look into more about that, you can of course look at page 400 and 407 in Donald Neiman's textbook. Another thing to mention here too is that we see these other capacitors in the circuit, and of course all capacitors are not bypass capacitors. These other two capacitors are actually coupling capacitors, and so that's why they're C sub C. And so these coupling capacitors are allowing AC signals to pass from one point to the next while blocking our DC signals.